It's a great pleasure to have Alexander Razborov from University of Chicago on our seminar. He is, I guess, extremely well-known expert in computer science and combinatorics of many fundamental results. And today he'll talk about limits of dense combinatorial objects. Thank you, Alexander.
Thank you for the introduction, Andrei. Good morning, good afternoon, good evening, good night, whatever. And I guess, like everyone else is struggling these days, trying to find something positive about all this mess. It's really a struggle. Usually I fail, but in this case, I can say something very positive. You can give a talk at Moscow Institute without having to beat Moscow traffic during rush hours. That's one very, very extremely positive thing. So, and so I checked the list of participants and I see many experts here. So I should apologize because another thing which sort of eroded is the concept of an organizer. What is Moscow seminar, right? It's sort of Moscow. So everyone can start his or her own seminar, but still I think the concept of an organizer is very important. So these are people who really do things. And they have asked me very explicitly to go slow and start with the basics, and that's what I will do. My apologies to the experts. However, since this talk is larger than usual, it's 1.5 hours, then actually I figured out that I will be able to do more novel stuff than I promised in the abstract. So I will talk a little bit more about our new work and perhaps even something that we are just writing down. So this is the main literature. This talk is based on the book by Lovos is just great. I highly recommend it. This paper of mine, well, it was not meant to be read by anyone. It was meant just as a point of reference. So if you read it, then it was a mistake. But unfortunately, I'm not sure that I know any good expositions of this stuff if you are new to it. So if you know of any good source, then please use chat. I would be really interested. And that's our new paper. I hope to be able to come to it. Right. Let me start with a few general philosophical points. So all classifications schemes like this, they are obviously superficial. Life is much more. Life is more diverse than any scheme. But still, if you look at what we are doing in combinatorics, then somewhat superficial, you can classify it into things. You either study exact structures, like, I don't know, graph isomorphisms or designs or whatever, or you do it analytically and you study things that are usually continuous in the sense that they are tolerant to small changes. And sometimes it even factors in the title of our discipline. Sometimes it is called combinatorics, sometimes it is called discrete math. Again, I don't want to give any definitions, but I think everyone here understands what I mean by that. And that's what we will be mostly doing in this talk today. So we will be really interested in things that are analytical and continuous. And I am sure there are more examples of intersection between these things. Right? I tried, for example, to do something extremal about this famous problem, open problem in algebraic combinatorics. I'm sure there are more examples, but still, these are the main threads in our discipline. We will be doing analytical things. And let me also now somehow define the scope of this research. Essentially, to get the theory going through from your setup, you need two basic things. The first thing is, of course, we have it always or almost always. So we want to be able to know when two structures are isomorphic. The second is actually not an easy, not a light restriction. It's a serious restriction. So it says simply that if I take any subset of my structure, then I will again get a substructure. And unfortunately, it excludes all or almost all, we will see one exception, almost all normal algebraic structures like finite groups, finite rings, whatever you like, with a few important exceptions. The theory is not applied to these things. But still, it can be applied to many things. Here are some obvious examples. So you can take any graphs, whatever you like, hypergraphs, directed graphs, vertex colorings, edge colorings are coming next. So, or you can confine yourself to some structures with forbidden substructures, like Turing-like problems in extremal combinatorics. So what else can you do? Before I tell you what else we can do, so let me give this very simple definitions. Turns out that this language is very convenient, and it is of course used by people doing many other things. We work just in the first order logic. And in order, let me go back, and in order to enforce these requirements, we need also to say something about our language, namely, first of all, of course, we absolutely forbid all quantifiers. We work only with universal first-order theories. And another thing is that function symbols like group operations are also forbidden. And so then we have our main property. It turns out that in this language, you can say basically everything you may want to say. So here are more examples. You can look at structures that you can look at models or structures that mix several different concepts. For example, you can look at graphs, ordinary graphs, and vertex colorings, edge colorings. You can formulate here all rainbow problems. This one is slightly more interesting. So assume that you have also a coloring, say vertex coloring into countably into finitely many, but unspecified number of colors. So it can grow with your model. The number of colors is not specified. Then, as it literally, you cannot do it in our language, because if you have more than finitely many predicate symbols, you are in trouble. But you still can, what you can do, you can put this equivalence relation simply corresponding to your coloring. It will be just one binary relation, and turns out that in this combined theory, you can talk about basically everything you may want about colored graphs, for example, where it's unlimitedly many colors. So if you add to your theory, base theory, linear ordering, then you will get linearly ordered models, of course, which is a very important in finite model theory. So you can mix and match things. Here is one more interesting example. So if you fix the dimension, then you can very easily talk about simplicial complexes. You simply introduce predicates for hypergraphs of all areas up to your dimension and write down obvious axioms. The first axiom is that it's really a hypergraph. We will talk about this axiom later, but it is always present in this area, otherwise again, it becomes ugly. And you impose symmetry. You say that it's really a hypergraph, and this obvious also axiom that says that a subset of a face is also a face. Then you have simplicial complexes, I guess. So, and now comes my exception, which is very important and very simple. So let's look at permutations, and the limit object, as we will see later, is called permutons, but let's now look at the permutations. And of course, permutations, they are functions. It's not clear how to represent it in this framework. If I, for example, take a subset that consists of these three vertices, there is no permutation induced by this subset. But if we look at our favorite textbook in linear algebra, or in algebra, I guess, then in that book, the permutation will be represented as something like this, which means in our language, it simply means that permutation is just a model of this theory. You have two linear orderings on the same ground set, and the first ordering is natural, and the second is given by your permutation. And then it completely describes your permutation, these two linear orderings, and we will see how it works a bit later in the course. So, by the way, if there are any questions, then please ask them. Sorry, what do I have here? So I have something on the chat. Sorry, it's technical. If you have any questions, then please feel free to ask them either on chat or just unmute yourself. Good. So that's the setup. So, and now again, a few general points of what exactly we are going to study here. So I basically already mentioned all these points. First of all, we are interested in really large combinatorial structures. And our plan is to make the theory a good theory that replaces this word huge by actually infinite combinatorial structures. And we are interested in not all, this is not all things that we study in discrete math, but it includes many parameters. So if I add, for example, one h to my graph, then you can change whether it is Hamiltonian or not. But you can change, for example, independence number by at most one. At most two, I guess. And I will explain it on the next slide. Somehow it turns out that so far the theory works much better for structures that are dense. Let me explain it using graphs as my example. And actually, let me also say that in the first part of my talk, I will mostly talk about graphs because it is the simplest thing and most studied things. So the H density of the graph is defined in the obvious way. So, and turns out that the dense regime where the density of your graph is supposed to be separated from 0 and 1, and you are interested, for example, we will see it later, in other densities, is one where the theory works best of all, and that's what we will do today. So in the sparse regime, Lovash called it, I think it was Lovash who called it graphinks. So it is the theory aimed at understanding, for example, regular graphs for a fixed constant d. The theory is also developed, but one of the most fundamental open questions is really hard. We don't know the answer, and it took really lots of time to do something interesting in the intermediate regime. For example, when the H density is something like that, and it is, of course, a regime that is of great interest in things like random graph theory. But recently, they have started to get really interesting results. I really like them, but still it's sort of work in progress. And in these two regimes, I am not aware of any work done for structures other than graphs. well, it's complicated enough even for graphs. But anyway, today we will mostly talk about this regime. Questions? Right, good. So if we are after defining something analytical, then of course the first thing we have to understand is what is the topology, what is metric, and how exactly close is close, what do we want to capture. And let me show you first one thing, which is very natural thing to try, and it does not work, but it does not work in very instructive way. So I really want to show you for something that does not work. And it is the most natural thing you can ask. It is edit distance. Assume that I have two models, two graphs, for example. And if they are on the same ground set, then you basically define edit distance by the number of edges that you need to align, to remove, to align, or add, to align them up to a permutation. So it's and if your models or graphs are on vertex sets of different sizes, then you use double stochastic matrices, which are essentially random, sort of, well, up to a permutation, right? It's better to describe it in probabilistic terms. You are looking at, at couplings between the vertex sets, and you require that both marginals are uniform, and then you define edit distance in this obvious way when you take the minimum over all possible couplings between these finite models. So it's a wonderful plan. There is only one but big problem. So it does not work. And there are different ways to explain why it does not work. Perhaps the simplest way, and I'm going to talk about it now, is just to look at random graphs. So if we look at random graphs, say P is 1/2, in the Erdős-Rényi model, then if you take any textbook in random graphs, then it derives one and only one point. This graph is essentially one object. It's random, but it's one object. It has as-defined properties. Whatever property you look, you can prove either formally 0-1 law or just determine the threshold. It is really for all practical, whatever it means, purposes, it is just one object. And edit distance does not know it. Because if I hit my button twice and I get two random graphs, then it is easy to prove. I think it's an old result by Erdős also, that you will get absolutely different results in the edit distance. It is too weak for our purposes. The topology it defines, and historically and also naturally, it is better to discuss what can we do about it? Should we really give up, or should we try to do something else? It is better to discuss quasi-random graphs. Of course, again, I apologize. I understand that most people here know about it. So, but it was a series of papers where these things were introduced. And let's start with some notation first that we will use all the time. It is the crucial piece of notation. Let me use this old-fashioned technology. So it is simply you essentially look at the random window in M of this size M, and you look at the probability that you will get something isomorphic to your model M, which is essentially the density probability, whatever word you like, that a random subset in N generates your model up to isomorphism. And for graphs, you can actually use many other notions. Right. So it turns out that the concept of graph homomorphism is very useful, or you can look at just non-induced subgraphs. or strong homomorphisms or labeled copies. There are many different options, but turns out that all of them are equivalent. So you probably are not, or you don't want to read. You don't want to read this part. It is an easy exercise. If I tell you, for example, the density of induced copies in your of H and G, then you can also count it stands for injective, the density of injective homomorphisms. These are very simple conversion formulas, or they are in Lower's book also. This thing is very interesting. It looks innocent, but it turns out that it is actually the backbone of the whole theory. That's what makes us infinite, what will make us infinite. It is a really very crucial point. So T of Hg is the density of all homomorphisms from H to G, and these are injective homomorphisms. And there is absolutely no nice formula that makes sense, that expresses one in terms of the other. You really cannot do it because you have to somehow, if you want to write an explicit formula, you have to take into account the probability that vertices collide under your mapping, and so it becomes a mess immediately. So that's how we actually go to the limit, by simply postulating that our graph G is so large that it does not actually matter. We can approximate well the quantity we are really interested in, graph homomorphisms, by its injective version. That is precisely what makes a finite world different from the infinite world. I am not sure I will be able to explain it better in this talk, but believe me, then it is really the crucial point. So that we can ignore, when we look at random mappings from H to G, we can ignore collisions. We simply postulate that we can ignore them. Good. So let's now compare these notions to edit distance. First of all, it is an easy exercise. You can do it, is that densities are obviously continuous in the edit distance. So in words, it means that if I change a few h's in my graph G1 to G2, then of course these densities are also going to change only, only proportionally. So it is Lipschitz. So it is, it will lead to strictly better topology. It's not zoology, it's topology. So, but before that, let me finish my example with quasi-random graphs. So let's make this strange definition. It's very strange because I just picked two graphs, just the H and cycle C4, absolutely arbitrary. Well, looks like they are absolutely arbitrary. Then, of course, if I have here, and this also G subscript M, and of course, if I have here Erge-Schrödinger graph, then we know expectations. These are the expectations of this homomorphism density, and it is very easy to prove sharp concentration. So for if it were true random graph, that's what would we expect. Let us postulate that my sequence, if I now have a sequence of graphs, that it is quasi-random if these two densities are about right. Okay, so why these two things? This explanation was given in this seminal paper. Turns out that it is equivalent to 10 or a dozen, maybe more now, other things that you may say about graphs that you expect to behave like random. And you can deduce even more if you don't care about equivalence, if you simply look in one direction. So it might be a bit too far-fetched analogy, but I would really like to compare this theorem with Kolmogorov complexity, right? What Kolmogorov complexity does, it tries to capture what does it mean that deterministic object behaves like random? Quasi-randomness does the same thing, but in totally different terms. So, and I just put as many properties here as I was able to fit on the slide. So, but believe me, then it's really good, and it's really right definition of quasi-randomness. Right. So, and now it was actually one of the motivations for all these things. Let's now move on. Now we give this definition, which is natural, or I mean, it is natural looking. And one message I want you to take home. Well, most of you are at home now, so I don't know what it actually means to take home in this situation. But anyway, that's what I wanted to remember, is that this is the right definition, and essentially I will try to prove it to you. So we simply say that we have convergence if whatever template M I take, finite templates, these densities will converge to some value that I will denote phi of M. So it may be slow, it need not be uniform, just converges, period. I don't impose any other restrictions on the convergence rate. So now one good thing, one immediate good thing is that we have compactness here. So it's well known, which means that if I have any increasing sequence of combinatorial structures, then I can always find in the convergent subsequence. Convergent sequences exist, and there are lots of them. And if you really insist on introducing a metric also on these things, then of course this is naive notion of distance. You fix any decreasing sequence of coefficients alpha m sufficiently decreasing sufficiently fast, and you can introduce this notion of distance just by averaging over all templates M according to this distribution. Of course, it is not very good definition. It's actually a bad definition. It is not used almost anywhere. It's the reason is because there is no natural way of finding the sequence alpha M. It's not natural, and this notion of distance is not very good. So let me also mention as a by-side remark that for ordinary graphs, we do have such a notion. It is called cut norm. I guess most of you know what it is. I will not stop it here. And it is actually also remarkable that it exists only for ordinary graphs. I don't know what would be a good notion of distance even for 3 graphs. And I think it's a very interesting open problem. And again, if you do this way, if you do it this way, then there is another problem which is serious, is that if you think about things like direct limits in algebra, it's not a direct limit. You have this sequence, and it might be simply, after all, it simply might be a sequence, a quasi-random sequence, which you obtain by sampling according to the Erdős-Rényi distribution. So members of this sequence are not connected to each other. Where do we go from here? Of course, we can do formal completion, like one way to define real numbers. You look at Cauchy sequences, you define equivalent Cauchy sequences, and then you call it limit object, but it's really not what we are after. We are after doing something natural, cool, and interesting, and mathematically sound. Good. So, and yes, and now it turns out that you can do, there's a striking analogy here with algebraic geometry. You can do it in 2 different ways. You either can try to describe your object or you can simply look at these sets of numbers, limit sets of numbers, and ask yourself, what do they satisfy? What algebraic relations, for example, they satisfy? Let's start with geometry. This is the notion that I'm sure is familiar to most of you. It's a graphon. So what is graphon? One thing to understand about graphons is that omega is not countable. We started with finite. We go to, for example, the interval or any other complete space. We skip countable sets on our way. And the reason is the same as here, because there is no such good thing as a distribution over countable set. Right? You can define discrete distribution, but it will give different values to different elements of this set. It will not be symmetric, it's not nice. So building this theory, we completely skip, well, not completely, we will talk about countable sets later, but now it is really analysis, something like 0, 1, and graphon is just what you think about it. The idea of this is that W of xy is the weight that you assign its intuition. There's no such thing. You cannot do it. Actually, there's no such thing as defining weights independently to all pairs. This thing is forbidden by the axioms of measure theory. It does not exist, but we still think about it this way. So it is the probability or the weight that I connect x and y, I connect within H. The intuition. So, and starting from this intuition, we can define densities of graphs in a graphon, which is basically like everywhere here. The recipe is always the same. You replace sums with integrals. You add those expressions dx, dy, dz that I have failed to understand in all my 35 years in mathematics, or 40 years. I don't understand what it means. The product or whatever. If anyone knows what this notation means, then please tell me. I have zero idea, but that's what people do. And everyone understands what we are doing here. It is just according to our intuition. I sample x, y, and z at random, and I draw these 3 edges at random with this probability, and it will be the chance that I will see K3. And the fundamental theory, which is very difficult, and it was even particularly difficult when they found it. Now we have, as we will see, other ways of doing it, but they used Simultaneous regularity lemma, is that actually, right, so I used P here, you can use T also, homomorphisms, that actually every convergent sequence of graphs, it converges to a graphon in precisely our sense. So the reversed statements, if I give you a graphon W, how to get a convergent sequence out of it is relatively simple. I just sample at random countably many points from my graphon, and I look at this sequence. And then you prove that under the product measure, it will converge to what we need it to converge to with probability 1. It will happen with probability 1, therefore there are only countably many templates. It will be your sequence with probability 1, and it also explains that a posteriori you can do it like graph limits. So you basically, it's a preferential attachment sort of. So you build your random graph vertex by vertex. You can do a posteriori, you can do it as a direct limit, but in order to do it, you have to know this very deep. There is absolutely no way around proving something like that. There is no easy way here.
Alexander, just a small question, yes. So just to make sure what convergent stand for exactly here, which convergence? This one, okay.
In densities, converges
Okay,
in densities. That's what we will study now. For graphs, you can give right another description as cut norms. It is also not easy. It's a couple of chapters in Lower's book. You can do it. For more complicated structures, it's the best we can do. More questions.
Great.
More questions. Good. So, and the last thing, if you want to call it a mathematical theory, is how unique it is. Maybe we just overkill or something like that. Turns out that we don't. So, turns out that just this set of numbers, densities in your graphon, or maybe probability theorists would have said higher order moments, they completely describe this structure. There is a caveat here. For some actually quite stupid reasons, you cannot find a measure preserving isomorphism between W and W2 itself, but you can do it like that, and it's good enough to show that it is even doable. So, and it's also very difficult. Even for graphs, it will be even more difficult in our case, and I will not say anything about the course. But anyway, now let me say a few words about the algebraic approach, Flock algebras. So, and it's not talking Flock algebras. It will be just a couple of slides. But the idea now is minimalistic. It's like when you do, for example, again, maybe it's far-fetched analogy, but when you do commutative algebra, you usually don't refer to geometry, right? You do manipulations in commutative rings. So let's see what we can do here. So first of all, it turns out that you can easily define an algebra, associative commutative algebra, and arrange this set of densities into homomorphisms from A to the reals with certain positivity conditions. And then turns out that we have cryptomorphisms. Cryptomorphism is the term we took from Lower's book. I think here refers to Berlekamp. I don't know the origin, but it's a nice word. It sounds very scientific. We use it. So these things are cryptomorphic in a good sense. So these abstract objects, they are the same as convergent sequences and the same as graphons. You can go between these three objects at will. So in a nutshell, if you do Flock algebras, then of course you have graphons in mind, but you will never commit to it on the paper. You don't talk about geometry, of course it's always the intuition, but you don't talk about it. And the question is, why should we dismiss such a nice thing as geometry? And the main reason is because, as many of you know, you can prove results in Flock algebra based, in extremal combinatorics based on Flock algebras. And in order to do it, you really want to be simple. Because all calculations that give you concrete results, they are always or almost always on the border of our computational abilities. If you, for example, don't use symmetry, then you are completely dead, you cannot handle it. If you do it using geometry, then you can do a few simple things, but you cannot do more results. So it turns out that if you need something from geometry, then you still can define it in this language. It's more ugly than in the geometric language. But what is most important is that you can do Flock algebras for arbitrary objects in the generality I described before. It need not only be graphs, and indeed by now, in my estimate, at least half of applications of Flock algebras is for combinatorial objects other than graphs. So that's. And let me just mention it here. one result which I really like. So, and it is quite, I think, intriguing. Simply says that all the things we've been doing, they are very simple. They look very simple, but they are algorithmically undecidable. So if I give you a simple relation about densities, or you can put here also, of course, you can put here graph homomorphisms. Instead of P, it will be the same because we have transformation formulas. Then it becomes undecidable, algorithmically undecidable. And moreover, well, I don't know if you know logic, but math logic, I mean. But the way you prove this thing, it actually gives you more. It gives you that there is no complete proof system for facts like that. So in the nutshell, no matter what is your favorite proof system or whatever you want, set theory, for example, if you want it to prove facts about densities for ordinary graphs with rational coefficients or integer coefficients, then it will be undecidable. It's a cool result. Anyway, as I said, it's not about log algebras, but I will need some of this notation later. If there are any questions at this point, it's a very good place to ask them. All right, good. Then now I am coming to our work. So what we are trying to do, we are trying to reconcile these two things and find geometric theory that would extend graphons and other situations, many other situations for that were done for specific structures. Many of them are here. So, and I apologize if I forgot something. We try to find some theory that would capture all the situations. So, and now that's where I thought I should sort of wrap up when I gave my abstract to the organizers, but I have half an hour more, fortunately, so I have time to give you some details about what happened. Right, so let me first tell you that most of this activity is really boring, which means that you take concepts that were known for previous structures and you generalize them. And we sort of view it as a service project. Well, someone has to do it, someone has to write it down, and I hope that we really put a lot of effort into trying to write it down. So as an indication, let me mention that our paper, it has more than 40 examples in it. So it's might be worth looking in, but I will try to focus in the remaining time. I will try to focus on those things that we have discovered that are more interesting and not quite trivial, 2 or 3 of them. But first we have, of course, the first thing we have to do is to see how to generalize it for at least 3 hypergraphs. And it is a very, very naive idea. Just replace 2 by 3 everywhere, and see what will happen. Is it a good idea? Turns out that it does not work. It also does not work. So, and this is a canonical example. Tim Gowers describes it in many of his texts. Other people discuss it. Let's look at the Erdős-Rényi graph, say with parameter 2, and let's look at the set of all triangles in these quasi-random graphs. So what do we get in this way? Then in this language, the most intelligent thing, you can say that you will get this hypergraphon, which is identically 1/8. There is nothing else you can say here, but turns out that each is the wrong answer. You can easily find, it's also an exercise, you can easily find a hypergraphon 4 vertices. so that its density, its frequency will be different in this hypergraphon and in this triangle set. So we really need higher order coordinates to do it. So, and to explain the way how to do it, I should start actually with the case that is understood quite well, with the case of graphons. So let me remind you that a graphon is just a symmetric measurable function like that. And I can replace this function with its graph. So, which is written here, it is simply, so if I fix the first two coordinates, then in the third coordinates, I will have precisely, well, the measure in the third coordinate will be precisely equal to the value of W, and you can do it in both directions. So if I give you an arbitrary measurable subset with these coordinates, then I can define a graphon out of this set just by taking the Lebesgue measure of all its induced whatever subsets, not projections, maybe projections, whatever. So it goes in both ways. And it turns out that to get a good characterization, it is precisely generalization, which is we have to represent things, even for ordinary graphs, in this particular way. So these are subsets now of this three-dimensional space. And you can retrieve everything you may want to retrieve from this representation as well. And in this language, for example, quasi-random graphon, W is always 1/2. You will get it like this. It is very simple subset, and let me know that it doesn't depend on the first two coordinates at all. And it characterizes. So if I have time to come to it, I will come to it. So, but anyway, it's quasi-random graphon. So, and now, let me immediately put it here. And now, let us start with the case of a simple predicate symbol, like ages. Then, for now, we let us now look at hypergraphons first. It is simply, right, for k equal to 3, now we have all these coordinates. A runs through all these subsets, the empty set is excluded for good reasons, everything else is included. And there is a natural group of symmetries acting on this space, on the coordinates. So hypergraphon is defined by Elek and Baller-Segedi is something which is invariant under this group. And we define PO, we simply remove this restriction. So, this is how our example works in this language. So these are new coordinates, and if you have not seen these things before, then it might not be easy to explain their exact intuitive meaning, but they are there. And so this is how we tried to describe our triangle graphon before. It is this set, and this is the right way, it is the right way of doing it. Namely, we look at these new coordinates we introduced, and we just say that we have this set of inequalities here. So, which is basically they correspond, as you saw it before, they correspond, these inequalities, they precisely correspond to the artificial graph. So again, it is a very non-intuitive point, but that's what you have to do to make the theory work. You introduce higher order coordinates, and then everything works out. Any questions about the definition?
Can you maybe say a couple more words about these coordinates?
I thought how to explain it. I cannot. No.
But at least when we would take a limit of objects, so
it is really, I think this is the best way to think about it. When if you decide whether to put your hyper H into your graph, into your hypergraphon or peon, then you look not only at one vertex subset of it, but also at two vertices. They have the same rights as vertices. These are generalized vertices. I thought about it, but you really have to play with it a bit. So,
okay.
Sorry. More questions? Okay, good. So now the next step is straightforward. Namely, if we now have a richer language, and in many applications we are interested in more richer language, if it consists of several predicate symbols, then we define what we call, I think for lack of better names, Euclidean structure. So structure is something which you use in the first order logic, but Euclidean structure is just, it's a good name. So, and at this stage, we still simply take a bunch of peons. For every predicate symbol, we have its own interpretation. And right now, let's not bother about about what we want, the relations we want to impose on them. Actually, we are going to bother about it on the next slide. So now we have a Euclidean structure, and we want, like you do in mathematical logic, you want to find an interpretation or truth set. You have a theon, or so for Euclidean structure, you have an open formula, quantifier formula, and you want to find its interpretation, its truth set. You want to define it. So, and here come a few subtle decisions that you have to make. The first decision is we try in different ways, we try to incorporate diagonal values as well. And the research before us, they also had tried it, it just does not work. You have to accept that if, for example, you want to talk about simple graphs, but simple with loops, if you want to have loops on your vertices, then the right way to do it is to introduce a new predicate for it. A new unary predicate that will describe loops. It is much better to separate loops from ordinary vertices, or ordinary edges. The theory works much better, so that's the decision we made. We don't even bother about these bad points. They have measure 0 anyway. We don't bother about them. So the next thing, again, I don't expect you to read it, but the next thing to define is the truth set for a simple for an individual predicate symbol, for an individual peon, and it basically says that all our definitions are very natural. So you can move them forth, or any subset of k is also a subset of n after you apply injective mapping alpha to it. Then you move it back on the coordinates, you move it once more back. It's a natural definition, and after you make it, you also say that your truth definition of truth simply commutes with all logical connectives like and or, and we don't care about quantifiers here. So you give this definition, and now comes the second important decision, and it leads to very interesting questions, as we will see in 5 minutes. It's a very important decision, namely, now we have a theory, obviously we have an axiom of our theory, obviously we want it to be satisfied in our structure, whether we want it to be satisfied just almost everywhere, or do we want it to be satisfied everywhere except for the diagonal. So these are two very different, not very different, but it leads to some interesting questions. And here we consider both options. We call it weak Sion and strong Sions. So if it is satisfied everywhere or almost everywhere. And now we can define densities in the obvious way. Namely, if I have a model M and a C on M, then I just look at all predicates that describe my model, take their conjunction, and look at that rule set defined by my model. Simply, basically, it is the complete analog that my mapping alpha does define set, and I look at the measure of this. So it's the density in this world, it corresponds to the density of occurrences of model M, which is difficult, just given the questions that Andrei already asked, because we have higher order coordinates, it's slightly less intuitive. But what is more important is that it works pretty well. First of all, we have completeness, right? So it describes convergent sequences of models just in the same way it was described before for all other structures, for all concrete structures, starting with graphs. So we have all cryptomorphisms. So if we have a Sion, then we can also look at this set of densities previously defined in the previous slide, and it will again give you a homomorphism in the algebra, like algebraic sense. So it again works in the uniform way for all series, and we also have Sion uniqueness, but it becomes very ugly and very complicated just because of higher order coordinates. But the idea is the same. You define a special class of measure preserving transformations that obviously preserve these densities, and then prove that actually in the opposite direction, which is very difficult, but you can do it. And let me also mention it here that somewhat surprisingly, you really need uniqueness to prove very natural things, and very natural things that should be proven naturally, but that's the only way we can do it currently. So, and let me give you one more description. I will not, it's actually the next two slides is how we prove these things. And essentially, there are three schools of thoughts how you can prove things with limit structures, basically equivalent. The first one is, as I already mentioned, is similarity regularity lemma. You can use ultra filters. Some people do it like Alex Sega did it using ultra filters, or you can use this also very difficult stuff from probability theory, which is called exchangeable local arrays. It's extremely difficult, but you can use it as a black box. You essentially put things into the right language and then you get it. And instead of talking about our proof, let me say a few words about this stuff. So now we do look at countable set, at the set of integer, for example. But instead of trying to define a probability measure on this set itself, we look at all, for example, countable models on this set. Then it's much nicer set. It's counter space, or it has barrel sets. You can talk about probability distributions. And if we have a Sion, then we can generate from it a distribution over countable models just in the same way as before. I sample countably many points from my Sions, and it will give me a probability distribution over this space. And turns out that it gives another description of this whole stuff. So, so what do we need? We need, of course, soundness, that with probability 1, we will get a model of my theory. We need exchangeability, that if I replace, or if I permute vertices in my countable set, then the distribution will not change. And we need locality, basically saying that what it says here is that if I look at different disjoint, mutually disjoint subsets in my set, then I will get mutually independent random variables. So, and once you impose these very natural axioms, 3 axioms, turns out that you get one more cryptomorphism. This set of objects is the same as convergent sequences, the same as seons, the same as log algebras, and you can give 2 or 3 more descriptions. One is using you replace locality, I guess, with ergodicity, and then you will get 1 more description. And so you can do also finding distributions. Anyway, that's the object we define. And so essentially what we use in our proofs is that the transition from local exchangeable arrays to seons, you can use this stuff about exchangeable local arrays as a black box, and it is very handy. Right, equations. Okay, very good. Then in my remaining time, I will just tell you more details. It is a bit more of abstract nonsense. So turns out that there is very, well, we use it in combinatorics, we use it anyway. We use open because we don't have any quantifiers here. We use interpretations between different combinatorial structures all the way, without maybe realizing it. So if I give any meaning to a predicate here, to a predicate, or express any predicate here as a predicate, as an open formula in T2, so that, of course, axioms go to theorems, then you get very nice concepts. So these are very good examples. If I have a tournament, every tournament is also a digraph. So we have an interpretation here, or just identical interpretation. Every graph is every triangle for a graph is also a graph. Every linear order is order. We have these interpretations. We can erase structures. For example, if I have any directed graph, then I can just ignore the, say, simple. Then I can just ignore all directions, and I will get an ordinary graph. And there are really lots of these things. Let me just show you one non-trivial example. If you look at the series of graphs and tournaments, they are very different series. And for example, they have different number of models, non-isomorphic models on 3 vertices, and it's an invariant, which means that they are very different. Actually, even on 2 vertices. This one has 2, this one has only 1. They are very different theories. What turns out that if I add linear order to both of them, then the theory will become isomorphic, and it's feedback, I guess, interpretation. So if I have a tournament and I have a linear order, then I can define this graph, which is obviously reversible. And one other point we make in our paper, well, I'm not sure that it is precisely the right audience to make this point, but I will make it anyway, that this transformation is natural. So it's a category, it's a functor, everything you do is a functor, and it's a really natural transformations between everything. In particular, if you prove anything about this theory, then you also have this theory, and in fact, it is what is implicitly happening in the next paper by Chang, Graham, and Wilson. It's not the one I refer to, it's the one that talks about random tournaments. To handle random tournaments, quasi-random tournaments, the way you do it, you use this isomorphism and graphs they had you had handled them before. Right. In my remaining minutes, I will show you something less trivial from what we did, and the first one is Euclidean removal lemmas. As I mentioned, we have these two notions. Weak theorem is essentially a model of my theory in this sense, where axioms are satisfied almost everywhere. Well, it should be A axiom. And strong theorem, where they are satisfied everywhere except for the diagonal. So, and removal lemma, I will comment a bit later on its relation to our normal favorite removal lemmas, is that if I give you a weak theorem, then you can rectify it by changing it on a set of measure zero so that it will become strong. And we prove it in our paper. So you have this rectification thing, which is obviously like finite removal lemmas. Measure zero corresponds to changing a few h's. And here is essentially, let me show on a couple of slides how we do it. So you can take omega whatever you like. It is convenient to remove the hands here. So, and then let's look at individual theorem, and we apply this basic fact, very basic fact from the measure theory, is that if you have any measurable set, then almost all points are already naturally classified in this set. It's Lebesgue density theorem. If I take my point and decreasing neighborhoods of that point, then for almost all points, it will converge either to 0 or 1. So we have good points in my P1 where it holds, and we have a set of outliers that have measure 0. And here is what we do next. So good points are already classified. We don't touch them. We have to rearrange outliers, those points where Lebesgue density theorem fails. And the way we do it, you can recast this argument in many ways, but that the one we liked is that I simply introduce propositional variables, just a variable, for any outlier in every P on P. Namely, if we take it or we remove it. It will be a propositional variable. There will be lots of them, continuously many, but we don't care. So then my rectification NP prime is defined by the value of this, by the values of these propositional variables. And the fact that it is strong, it is now formulated as simply constrained satisfaction problem on those variables. And voila, we now apply compactness principle. We prove that any finite set of these constraints can be satisfied. It requires a work, but not much work. And after we do it, we can claim that compactness by compactness of propositional calculus, so the whole bunch of constraints, uncountably many constraints, lots of them, but they are still satisfied. They can be satisfied, and it gives you theorem and paper. Is it a good proof or a bad proof? It depends on your attitude, because it looks simple, but it is totally non-constructive. It is axiom of choice. Compactness principle in propositional logic is equivalent to axiom of choice. I think I will just finish this thread, then we'll wrap up. So, and if you don't care that much about mathematical logic, then you can also ask the same question in this simple form. The theorem we get at the end is not necessarily Borel. even if you started with Borel n, this thing, well, you can always start with it because it's almost everywhere. This thing is not necessarily Borel, and it's open. Whether we can always find it constructively, do it constructively, find it Borel. These are two cases where we were able to do it. The first case is what is called in logic Horn theories. So if all your axioms have this form, where P and Q are, I guess, positive. Yes, P and Q are positive formulas. If you do it this way, if all axioms are of this form, we can prove it. And even for linear order, it required several pages of proof. I give you a linear order, which is linear order almost everywhere. Can you constructively fix it so that it will become linear order everywhere? It required several pages. And here is what I can say about it. So, and this question, I think I was able to reasonably trace it to Lovash. He had asked it about it at some point. It is the simplest theory where we don't know the answer to Borel inducibility or to Borel removal lemmas. You just forbid C4, but induced copies. We don't know if it is Borel. So now, as I said, it would be very nice to somehow rephrase it in terms of connections to finite induced removal lemmas. So Austin and Tao did it in their work, and so I hope it can be also done here. And it is now reverse mathematics. I would not be surprised if actually our Borel-induced lemma is simply equivalent to some reasonable version of the axiom of choice. So, not Borel, just induced lemma, understood as a logical statement, it might be simply equivalent. So now, how much time do I have, Andrei? I have this.
You have 15 minutes.
Oh, 15 minutes.
minutes.
Good. No, it's the same thing, because I saw on your obsolete website that it's in 15 minutes I will do everything.
Yeah. Great. And if you need more time, then you.
No. 15 minutes is just. I have essentially this one more topic, but it is cool, and I would like to go over it in details. So let me. Permutons, it is the concept that was introduced in this paper, and it captures convergent sequences of permutations. In business as usual, so I have a sequence, I have a template, L is fixed. I have a template permutation, sigma. I look at an increasing sequence of permutations, and I look at the probabilities or frequencies. If I restrict my tau to L randomly chosen points, then the probability that I will see sigma, and they describe it in terms of permutons. What is a permuton? It is just a measure on the square, such that both its marginals are Lebesgue measures, both here and there. And so the idea is that if I want to calculate this density, then what I do, I pick at random according to the measure mu 4 points. According to this measure, order them, for example, like this picture, in the increasing order according to the second coordinate. And then I look at the first coordinate, it will be at the permutation 2, 4, 3, 1. So that was the idea, and it's, as always in this business, it requires lots of work to prove that it really converges to a permuton. So what we can do, we can, it has to be expected because both terms here describe convergent sequences of permutations. So these two things are also cryptomorphic, but what we do, we give a very natural cryptomorphism here. So how to construct a theon, what is a theon in this in this theory, it is simply a couple of linear orders on my ground set. I take as ground set the same square, omega squared. I take this measure mu, and you have to prove that you can take arbitrary measure and almost arbitrary ground sets, but it's also technical, but it's not very difficult. But after you do it, you can simply define my peons corresponding to linear orders in the natural way. I just compare coordinates pi1 and pi2 are these two projections. I should have written it here. Pi1 and pi2 are these two projections. So, and then you can treat permutons uniformly like you do all other structures. Another example are limits of interval graphs. So what is an interval graph? Let me remind you, you have a bunch of intervals on the real line, and it's the intersection graph of those intervals. So before we treat it, let us make this simplifying assumption. Since this concept is inherently topological, then we can assume that left ends of my intervals are just uniformly spaced in 0, 1. So it does not change anything because it's a logical concept. And then interval graphs are described as limits, as was explained in that paper. Now it is a probability measure of this triangle because left and always should be smaller than the right end. And now it is two projections. But now we require only one of them to be only one marginal distribution. We require only this one to be Lebesgue, uniformly Lebesgue measure, and it precisely corresponds to this restriction. It is captured by this restriction. R can be arbitrary, of course. And they discussed it also in their paper. You can also define it as graphons. Instead, we can define it as graphons just in the natural way. My omega will still be where my measure mu lives. And the graphon will be defined simply. I still want to define it in this way. Again, we ignore higher order coordinates, which means that my graphon is 0, 1 graphon, and it is defined in this way. So, and right, let's look now at what is happening here. The theory of interval graphs, you can form the theory of interval graphs. Turns out that it can be, well, every theory that is closed under submodels. It is obviously, it has an axiomatization. It can be made explicit. It's not very easy, but there is an explicit axiomatization of this theory. You need to forbid induced cycles, large induced cycles, or they may not appear in an interval graph. In any interval graph, you can check it. And a few more graphs, you will get explicit axiomatization. But anyway, now we also have an equivalence between, or cryptomorphism between all these options, simply by looking at seons in this theory. So you look at all seons in this theory, at everything that satisfies its axioms, and again, a posteriori, it should be equivalence to limits of interval graphs in their sense. But the point here is that we bypass convergence sequences. We give quite natural transformations and non-trivial points. Non-trivial part in both cases is if you have a seon, how to construct from it a permuton or limit of interval graphs in their sense, and to do it by an explicit construction. We know that it can be done in principle, but the point is that we want to do an explicit construction for it. And after you do it, again, there are, I can see lots of merits into giving ad hoc limit objects, defining ad hoc limit objects in specific situations, but it's also nice to know that you actually don't have to work. And it follows existence and uniqueness, which is hard to prove in all those cases. It also follows from general theory. So interesting stuff. 3, which is natural quasi-randomness. We are still writing it up. It is some application of the theory to quasi-randomness. If I had time, I would have probably said something about it, but perhaps my time is almost up. I hope there will be questions, and let me stop here. And thank the organizers again.
Well, thanks a lot, Alexander, for this very interesting talk. Are there any questions?
Have you tried to model Gromov-Hausdorff limits? Like every path metric space is a limit of the graphs in some sense?
I thought about it, and I think I see some complications. Let's take it offline. It's certainly something to try, something to think, but there might be complications.
Thank you.
Let's take it offline. I have to think about it, and I will write to you.
Great. Other questions? I actually have one myself, so maybe can you say a couple more words about how uniqueness is proved, at least in the graph case?
In the graph
for the limit object.
It's difficult. It's difficult essentially. You either have to use quite deep measure theory. Ideologically, it can be considered as high-dimensional generalization of the theorem that says that every random variable is uniquely described by its moments.
Mm-hmm.
So, and the proof is really complicated, and it uses very serious measure theory. I cannot comment on this proof immediately. So we do it, fortunately, we do it after we can use very fortunate to us, we can use reuse. It's a whole book by Kallenberg. We can reuse the stuff from exchangeable local arrays. So I think you don't need exchangeable to be unique, but I'm not quite sure about it. Maybe you know. So it's really difficult, but we were lucky that he, in his book, he essentially does it in a context very similar to ours, so that we can use it off the shelf. So I can see something else here.
Yeah, it's a question to us, I guess. There will be. I'll quickly answer. There will be a recording appearing on the YouTube. I'll send the link to the YouTube maybe now. So this
Sasha,
is the link where you'll find in a few days.
Yes. So as you know, the theory of limit structures is a powerful tool in understanding extremal behavior of these combinatorial structures. It's also been quite a good tool for understanding typical behavior of structures, right? So you have a large structure, a large random structure with certain properties, and you want to know what it looks like. And it's been useful to have variational principles as we have for graphons and permutons, for example. And it seems that such principles ought to hold in some generality, and maybe they're preserved in some sense by your cryptomorphisms. Is it possible that we can extend some whole theory of these variational principles to theons or whatnot?
It makes this question makes perfect sense. We simply did not have time yet to think about it because it took literally several years to try to write it up because we tried to do it right, not just yet another text where we try to make it accessible. So it's an excellent question. Now when this year, at least the language is out there, it's an excellent question. What you can do with this language, but so far we thought only in the direction of quasi-randomness. But it would be a very good direction to try.
For a wonderful talk. This is great stuff.
Thank you.
Great. Any other questions?
I think I see something here.
Yeah.
Right. So maybe what can I say? We really I know what you're implying. Maybe yes, maybe no. But when you start looking at more complicated structures, then really everything becomes a real mess. We already saw higher order coordinates. So as far as I know, people didn't try it, and I think it's a very good thing to try. It's about thermodynamics.
The follow-up to it is there a toy model one could try first to this?
3 graphs. 3 graphs. 3 graphs is very natural thing. There is a huge distance between graphs and 3 graphs. Somehow I am not aware of any principal differences between 3 graphs and arbitrary hypergraphs. And if you are interested in non-symmetric structures, then directed graphs is something also to try. So in one direction, when you increase dimension, it's 3 graphs, and when you remove symmetry, it's directed graphs.